As we've seen, entropy tells us something about the spontaneity of processes, and it's related to also the efficiency of the work that we can get out of a thermodynamic change process. And this is really exemplified by the work of Carnot in the early 1800s, and he developed something that we now know as the Carnot Cycle to really get at the heart of this. Now, in order to talk about this, I'm going to set up a PV diagram so that we can chart what this looks like when it's graphed out. So I'm going to make it big enough that I can hopefully draw the things that I need to draw in here. As the name suggests, the Carnot cycle is basically a cyclic path that a process could follow, but it's made of several well-defined steps. I should also mention that this path, all of the steps are reversible, and so since they're reversible, we're able to draw them on a PV diagram. So the first step in the Carnot cycle is to do an isothermal expansion, and this will take us from our initial point P1 V1 to a new point P2 V2 at a temperature which I'll call T high. Alright, so let's draw it up here on the diagram. So I'm going to put it way up here. So we're following an isothermal path, so it'll go something like this, from P1 V1 to P2 V2. And just to help me refer to these things, I'm going to call this point 1 and this point 2. And I've referred to this as path A. So when I refer to points by numbers and paths by letters, hopefully you can follow what I'm saying. So what's going on in this initial path? Well, we're starting up here at this point. We're not going to change the temperature, but we are going to perform work. Because remember, anytime we have an expansion, the system is performing work on the surroundings. Now, it gets that energy to do that work from the heat that the system has. So you can think of, in some sense, the system has derived a bunch of heat from, from its point here on this isotherm, and it's now going to take that heat and make work out of it. Now, the second step of the Carnot cycle involves an adiabatic expansion, and this is now going to take us to a new point P3 V3. So we're going from P2 V2 to P3 V3, and it doesn't have a constant temperature, but I'll remind you that on an adiabatic path that means that we don't have any heat exchange happening. Remember also that adiabatic paths tended to be a little steeper than isotherms, so I'm going to draw it very steep like this down to point 3, and this is P3 V3. Alright, so what's going on here? Well, we're still doing work. The system is still doing work on the environment around it, but it's no longer taking that heat from itself. It's no longer converting its own internal heat into work. In essence, what's happening is we're changing isotherms. We're going from a high isotherm to a lower isotherm down here on point 3, and the heat that the system is absorbing from, or that is releasing from this change of temperature is going directly into performing the work. Now, the third step in the Carnot cycle is an isothermal compression. And what we're going to do is we're going to follow an isotherm back up, kind of back up toward where we started. But our isotherm now is at a temperature T low. And I should have labeled this second path B over here. So T low, it's at a lower temperature, and this is in keeping with our understanding of isotherms, that the higher temperature ones are the ones farther out here, and the lower temperature ones are the ones closer to the origin. So this isothermal compression is going to go from P3 V3 to P4 V4. It does not change temperature. That temperature will stay at T low. But because we're compressing the system, it's now the surroundings that are doing work on the system. All right, so that's the direction of the workflow in this case. And I should probably put little arrows on these to indicate the direction that we're going in each of these steps. The fourth step, I hope it's not a surprise, is another adiabatic step. In this case, this is an adiabatic compression that takes us back to our initial point. So in other words, we have to choose this point, and I haven't labeled it here on the diagram. We have to choose this point so that an adiabatic change from it will take us right back up to our initial state. And I should also label the path down here C, and this is path D. So this adiabatic compression is just going to take us from P4, V4 back to P1, V1. And again, we'll encounter a path that has no heat exchange with the environment. So you'll see pictures like this often in thermodynamics books, because the Carnot cycle is really a classic example of a thought experiment that actually helps us to learn something about how thermodynamics works and how it may limit our possibilities. In particular, we can tell from this, we can determine the engine efficiency of this kind of cycle. Now, this cycle is, in some sense, inspired by the steam engine. Carnot was very interested in steam engines and in what made them efficient and not efficient. So, in effect, what a steam engine does is it raises steam up to a very high temperature. That steam is then expanded. That expansion performs work. It basically turns the steam engine over. And then you have to cool off that water so that you can heat it up again and start the same cycle again. So in essence, the water is the thing that's going through this cycle. And as the water goes through the cycle, we're converting heat to work in the first couple of steps, and then we're taking that and reheating the water back up to the high temperature again so they can go through the whole process again. So what Carnot was interested in was, how efficient can we make this? Can we make basically a perfect engine so that all the heat we put in turns into work that will drive a locomotive or some other process? Well, it turns out that we define the efficiency of this process by the following fraction. What we're going to do is evaluate the heat that we put in. Okay, that's the cost that we're devoting to this process, and we're going to put it in the denominator. And what we're going to put in the numerator is the work that we got out. And I'm going to write that as negative because from the system perspective, the negative work is the work that it's performing on the surroundings. So in essence, we're defining our efficiency as the total work that we're getting out of it divided by the heat that was absorbed in the first step. All right. Now, in that first step, well, first of all, the work that we're getting out of this is the work that's going through all four steps. So it's WA plus WB plus WC plus WD. And we know from our examination of cyclic processes that that's just going to be the area inside the cycle. Now, since we're going clockwise around this cycle, it's also going to be less than zero because the system is the thing that is doing work on the surroundings. So we necessarily, and this is equal to total work, so we necessarily have work is less than zero and the heat is greater than zero for this sort of process. All right, now how do we relate all of this to what we're measuring up here? Well, remember that for a cyclic process, a state function like U has got to be equal to zero. So our total heat has to be equal to the negative work that goes through this. So they have the same magnitude, but they're going to have different signs. Now, in this four-step process, I've got two steps, the B step and the D step, that don't generate any heat at all. So the total heat for this mechanism is just QA plus QC. But I also want to make a distinction here. In QA, I was gaining heat from the process because the work was negative. So this one is greater than zero. But in QC, I'm doing work on the system, so I'm going to end up adding energy via work, so QC has got to be less than zero. I'll also point out that since these things are taking place in isothermal processes, that in those processes, so for QA, that's equal to negative WA, and for QC, that's equal to negative WC. So the work is, remember, the area underneath the curve, and the work in A is greater than the work in C, so the magnitude of WA is greater than the magnitude of WC, and so the same is going to be true for the heat exchange. All right, this has all been a long-winded way of saying, okay, so if Q is equal to minus W, and it's equal to QA plus QC, then I can put that up here and say that the efficiency is just QA plus QC divided by QA. But QC is less than 0. So in fact, this is going to be a fractional number. This is always going to be a number less than 1. So in other words, I'm always going to have an efficiency that is not perfect. I can never achieve perfect from this unless I somehow was able to have my low temperature occur at absolute 0, but no one has figured out exactly how to do that. But I'm always going to have a limitation to how efficient my engine can be. We can actually use thermodynamics to reframe this in terms of the temperatures, and we can write basically that the efficiency of the engine is related to 1 minus, oops, let me write an equal sign here, 1 minus T low divided by T high. So the best we can do is, like I said, when we go to a temperature of absolute 0 for our low temperature, which would be here at the bottom part of the curve. Now I wanted to make one other comment, and that is that we've been investing a lot in our description of PV diagrams, but there's another kind of diagram we could also draw that's related to this. And I'm going to call this a TS diagram. We've introduced entropy now. It's a property of the system. It's a state property. What does this cycle look like in a TS diagram? Well, in the first step, we've got constant temperature. So this is T high. So we're basically going constant temperature across here. In the second step, so this is the A step. In the second step, we've got dq equals 0, so that means that there's no change in the entropy. So we're going to go straight down. We have a constant entropy process. So this is step B. In the third step, again, it's an isotherm, so we're going to go across and maintain temperature constant, but now it's going to be maintained at T low. And finally, we're going to end with another adiabatic step, which will take us directly back up to our initial point. And again, that is a step that doesn't have any change in entropy. So you'll see that, in fact, these two cycles on these different diagrams actually represent the same process. And because this now, actually this process, the area inside here represents the heat change for the process, and the area inside here represents the work change for the process, we have a cyclic process that has delta U equals 0, so in fact the total heat plus work, which is the change in U, has to be equal to 0. So that means that the area inside this curve and the area inside this are equal to one another. It's kind of an interesting sidelight on the whole issue of the Carnot cycle, but you should read carefully the passages that you have in the text on this. I've just scratched the surface in describing the Carnot cycle, but it was really a land-breaking event back in the early 1800s and really helped thermodynamicists understand a lot better how these different kinds of systems could work.